Today's lecture is on band-limited signals and sampling. In this lecture, we will talk about the definition and examples of band-limited signals, and maybe the most important result in this lecture is the sampling theorem, also known as the Shannon-Nyquist sampling theorem. And then we'll talk about impulse train sampling, and we'll study it in the time and the frequency domains. And then we talk about aliasing and how it arises from undersampled signals. A band-limited signal is basically what the name says. It's a signal. It could be continuous or discrete, where the spectrum of it is limited to a finite interval, meaning when you do the CTFT of it in the frequency domain, it may look something like this thing here. So I'm trying to draw an example here. So it could be something like, so if this is j omega, let's say, and this is 0 here. So it may look something like this. But at least you know that it's going to be 0 starting some point here. So for example, if this is, let's take some values. If this is, let's say, 100 and this is minus 100. So this is a band limited signal with here the bandwidth is 100. It depends how you want to count the bandwidth, but here the limit, the cutoff bandwidth is 100, meaning above 100 is 0 and below minus 100 is also 0. So again, a signal is called band limited if in the frequency domain there is a maximum frequency and a minimum frequency, and beyond these frequencies the signal does not contain any frequencies. Again, the shape of the spectrum can be anything. Maybe usually we will take it to be a triangle, just to take a general shape, but it can be anything. And the motivation here is that many signals that we have to deal with in engineering applications, they are band limited, such as maybe a recorded audio or a video or a recorded song. So you know the human voice, or when humans sing, they can only reach certain frequencies, so which makes the signal, the recorded signal, a bandwidth limited signal. Also, when you look at the spectrum of light, the things we can observe is also limited. So for this reason, studying band limited signals is very interesting and very important in practice, but it turns out that they have a very, very interesting property when we sample them, and that's basically the main thing that we're trying to, the main goal that I want to get to in this chapter. Let's take some examples. So if you take examples in the time domain, for example, if you take this example, x of t is e minus at ut. So we did lots of these examples in the different type of transforms. So you know, in the CTFT of it, x of j omega is 1 over a plus j omega. So if you take, for example, the magnitude of it, so here, x of j omega, right, it's going to be 1 over the magnitude of a plus j omega, so it's going to be, if you wanted, 1 over square root of a square plus omega square, and you know that this is not bandwidth limited, so this is going to be looking something like this. So for omega 0, for omega equals to 0, this is going to be equal to 1 over a, and then when omega goes to plus infinity or minus infinity, this is going to 1 over a. When omega goes to plus infinity or minus infinity, this is going to go to 0. So this looks like this, and it goes to infinity. So, which means that the bandwidth is not limited, and this is not a band limited signal. Whereas if you take x of t equal to sine bt divided by pi t, then you know, hopefully by now, that this is actually in the frequency domain, this is a low-pass filter. So this is basically the impulse response of a low-pass filter that cuts all frequencies that are above B. So in the frequency domain, maybe this is the simplest example of a band-limited signal, is going to look something like this. So it's going to cut everything that is above B and below negative B, and so it is band-limited. Here we have same examples in the discrete case. So we have x of n equal to a n u of n, and then when you do the DTFT, so this is the DTFT here because it's a discrete time signal, so you get DTFT of the signal 1 divided by 1 minus EJ omega, and again, it's clear that it's not bandwidth limited, whereas if you take the low-pass filter in the discrete time also, it is, you're going to get, this will give you also a band-limited signal. So one thing to keep in mind is that if a signal is finite in time, meaning it has a finite support, then it cannot be band limited. So if you have a signal that is, let's suppose, a box in the time domain, and we did this many times in many examples, then it cannot be, for example, for this signal here, the DTFT or the CTFT is going to look something like this, and it's going to extend to infinity. And this applies to all signals that have finite support in the time domain. So if a signal has a finite support, so you cannot have a signal that in the time domain, time, and this is frequency. So you cannot have a signal that looks like this in the time domain and also look like this in the frequency domain. So if it is, so this will never happen. So if it is bounded in the time domain, then in the frequency domain, it will extend to plus and minus infinity and vice versa. For example, again, we go back to maybe the canonical example we look at is the low-pass filter. So, right, it is bounded. It has a bounded support, if you want, meaning it is non-zero only in a finite interval. Then, in the frequency domain, it goes to infinity, right? It goes from minus infinity to plus infinity. So, in some sense, you cannot have a signal that is bandwidth limited, that is limited in the frequency domain, and also limited in the time domain. So if you make it limited in one domain, it has to be extending from minus infinity to plus infinity in the other domain. This is just I won't prove this, but it's something to keep in mind to check your answers against, or even to, whenever you work an example, to keep it in mind so you can check this against the example you're working. The main result that we will see in this chapter is that there is a very important characteristic of band-limited continuous time signal. And that is that if we have a continuous time signal that is band-limited, then we can just store or process the samples of it, and that's enough to recover the whole signal. Meaning that if you, let's take an example. So suppose that we have a signal that is band-limited. So let's suppose the signal is this. Something like this, and suppose that so this is in the time domain, and let's suppose in the frequency domain it's band limited. Then one of the main theorem that we talk about, the sampling theorem, it says if we sample this signal fast enough, and we will explain more later what do we mean fast enough. So if I just take the samples here, and I've just stored these samples, then just from these samples, so I have now the discrete signal that is in red. So just from the discrete signal that is in red, and these values at these discrete values at these different sampling times, I can recover the blue signal. All the blue signal with no error, no distortion. I can recover it exactly. So, and this is called the sampling theorem. So the sampling theorem says that if you have a band-limited signal, all you have to do, you can just sample it, and then from the samples, these numbers, which are discrete, so you can go from continuous to discrete time, which are easy to process in any signal, and apply any signal processing algorithm on them. You can recover the original signal, the original continuous signal. So, and this is really surprising, a surprising fact. And this is here stated in more details. It's called the Nyquist-Shannon sampling theorem. And I'm going to try to go over it real quick here, and we will revisit it again. So this, I just want to give you kind of a flash forward of the main theorem that we're going to see. So it says that if x of t is a signal whose CTFT x of j omega, or whose CTFT is band limited, so the spectrum is 0 for when the magnitude of omega is greater than omega 0, so it's 0 for all frequencies that are larger than omega 0. Then x of t, which is continuous, is only determined by the samples of its samples at time taken at intervals of t. So here I'm sampling every t seconds, let's say. So let me maybe draw it here. So I have the signal. Let's suppose I have my signal here. And I'm taking, suppose that this is 0, so I'm taking samples every t seconds. So 2t, 3t, 4t. So all I need, the sampling theorem says, is all I need is these values at t, 2t, 3t, 4t, and also in the negative, when you're going in the negative direction, then I can recover the signal. Now, the very important condition, which is actually the main message of the theorem, is that you could recover the signal only if you're sampling fast enough. And by fast enough means that your sampling frequency has to be twice as big as the maximum frequency in the signal. And this is called the Nyquist rate. So if you know that your signal, the maximum frequency of your signal is, let's say, 8 kilohertz, then you have to sample at a frequency that's larger than 8 kilohertz, then two times 8 kilohertz. So you have to sample at a frequency maybe 20 kilohertz, anything that is strictly larger than 16. So basically that's the main result, is that if you sample larger than twice the frequency, the maximum frequency that you can recover the signal, you can recover the continuous signal just from the points. And in the next slide I will show you why this is surprising. Again, the main message here is that you have to sample at twice the maximum frequency, and we will see why later. Now, to see why this is surprising, let's suppose I sample a signal, and I give you the samples, and I ask you to reconstruct the original continuous signal. So mainly what I have here, I'm going to give you, let's say, I'm going to give you the yellow. These are the signals, right? So I'm looking at the figure below. So I'm giving you these samples here, the yellow ones. I'm just coloring them again. So this is what I give you. This is the input. This is the puzzle that you're asked. I'm giving you these points. So this is at 0, this is at t, 2t, 3t, 4t, and so on and so forth. So you're given these points, and I'm asking you, and the question is, can you recover the continuous signal? I don't think you need to think a lot to realize that actually it's almost an impossible, in general, it's an impossible question, or it's kind of an ill-posed question, because there's an infinite number, maybe an uncountable number of signals that can go through these points. And here there are, just for illustration, there are the figure gives three different signals, blue, green, and red, that go through these points. And of course you can draw an infinite number of them. So I'm gonna draw another maybe blue one here. So you can have this signal maybe. Right? There are an infinite number of signals. So the question is, how can I exactly recover the continuous signal just from the samples? Of course, the sampling theorem says you cannot always do it, but if you sample fast enough, meaning if you sample omega sampling, which is 2 pi by t, t is the period of sampling, you're sampling every t seconds, should be twice as the omega 0, the maximum frequency. If that is true, then you can recover the original signal. And again, this is what I want to show you. But the goal here is that to tell you why this is interesting, or why this is a surprising fact. Now, how can we write this sampled signal mathematically? So I'm going to look at what is known as an impulse train sampling, meaning I'm sampling by using a train of pulses. So here I'm sampling using the signal p of t, which is sum of delta functions, sum of impulses that are spaced by t. So this signal looks something like this. So you have at 0, at t, at 2t, and so on and so forth, and also at negative t, negative 2t, and so on and so forth. So it's a train of pulses, of deltas, right? And now what does it mean to sample a signal is, what it means is that you're actually multiplying your signal x of t by this train of pulses. So in the end, what you get is what we call the x, this is the sample signal, and it has this form. So when you multiply it by the impulse train, it's just picking up the values at multiples of t. So it's going to be the discrete signal at time equal to multiples of t at nt. So let's take an example. So let's suppose your signal is this one, right? And then when you multiply it by the impulse function here, so you're going to get this signal here. So that's basically xp of t, right? And again, the goal is, the interesting fact is that this is easy. Going from here, this direction is easy. Sampling is easy. The question here is how from the sample signal I can recover back the continuous signal. Okay, now mathematically this is what you need to know here so far. So let me erase this, and mathematically you need to know how to write the sample signal, and I'm going to write it this way. So the sample signal is actually an impulse train multiplied by the original signal, which is the summation of x of nt delta t minus nt. So it's just picking up the impulse function, the impulse train is picking up the values of the signal at the sampling instances. So like I said, this is what's happening here. So you have the original signal here in green, and you hit it with the impulse train. So what it does, you kind of modulate the impulse train by the magnitude of the signal at the sampling times. So you go from the original signal here. So this is the original signal. I mean, you can think of it as an audio signal if it helps, to a sample signal. So this is maybe a magnetic recording, an analog recording, and this is the digital recording that is sampled. So this is the sampled signal. Again, the holy grail here is that how can I from the sample signal, how can I recover the original analog or continuous time signal? And it turns out the answer lies or becomes easy to understand how to get it if you look at what's happening in the frequency domain. So again, my sample signal is xp of t, which is the sum of the impulse train modulated by the value of the signal at the times at n times t. Now we can use the multiplication property of the CTFT, and we know that multiplication in the time domain actually gives convolution in the frequency domain. And don't forget the 1 over 2 pi factor outside. So now I know that the spectrum of the sample signal is going to be essentially the spectrum of the original signal, which is x of j omega, times the spectrum of the impulse train, right? So if you're confused, so this is the original signal that I'm interested in, and this is the CTFT of the impulse train. So we need both of these spectrums. Now again, the spectrum of the bandlimit signal is going to depend on the signal we're working with, but as a generic representation. We pick here this form. So the important thing, it doesn't matter what the signal is or spectrum is doing between negative omega 0 and plus omega 0. What matters is that it is limited to this interval, and outside this interval is the spectrum is equal to 0. So this is band limited signal. So again, so I'm just taking this triangular form as just an example to represent the signal. It depends, it's going to depend on your signal. The remaining question is, what is the frequency, in the frequency domain, what is the CTFT of the impulse train? So the CTFT of the impulse train is actually, the impulse train is a periodic signal, and you know from even the DTFT times or lecture is that the CTFT, or in the frequency domain, periodic signals become also, in the frequency domain, they are also impulse train. So you can show that Pj of omega is also an impulse train, separated at multiples of omega s, where omega s is 2 pi by t. So this is your sampling frequency. So you start from P of t being this. So this is 1. So you're sampling every t. So this is P of t, the impulse train in the time domain. And in the frequency domain, so you're going to get the same thing, but it's going to be scaled by 2 pi by t. So I'm going to get here 2 pi by, or maybe let me erase this. So I'm going to get, here it's 2 pi by t. And again, I'm going to get an impulse train, but separated, instead of in time, they're going to be separated by the corresponding frequency. So the sampling frequency is omega s here. So it's omega s, 2 omega s, and so on and so forth. And you can find more information about the proof in the textbook. But I think I did this in more details in the discrete time. But if you need more information, you can look in the book. The main fact here is that the CTFT of an impulse train in the time domain, it's an impulse train in the frequency domain. Now to get the frequency spectrum, the spectrum of and the frequency domain of the sample signal, then I have to convolve the signal here, right? So this is my signal x of j omega, and I need to convolve it with an impulse train. So this is p of j omega, and here it's omega s, which is the sampling frequency, right? And you have a term, don't forget, 1 over 2 pi. And we know that when we convolve a signal or a spectrum by an impulse, it's just going to shift the domain. It's going to shift the spectrum. And this is what I get in the frequency domain. I'm going to get this important phenomena. So it's going to be equal, the spectrum of xp of j omega, which is the spectrum of the sample signal, is going to be a repeated versions of the spectrum of the original signal shifted by omega s. So that's what's going to happen. And I have to add these things together. So I have copies that are centered around omega s, multiples of omega s, and these copies are added together. Therefore, I have two cases. It depends on how the omega s compares to omega 0. So if you remember here, if you go back to the previous picture, what did I have? So what I had here, so let's suppose my original signal was centered at 0, and you had here omega s and minus omega s. And you know that the other copy, sorry, here omega 0, right? And here centered at 0. You know that the other copy is going to be centered at omega s, right? Now these copies will not overlap, right? When will they not overlap? These copies will not overlap, and this is very important. So this is basically the sampling theorem. these things will not overlap if basically omega s, right, is greater than 2 omega 0. So the extreme case is this. So you have here omega 0 and then omega 0 here and omega 0 here. So omega s is equal to omega 0, and this is when they will overlap at one point. And this is how you get basically the sampling theorem, but we will get back to this. But let's understand here that there are two cases. The cases where the copies will overlap and the cases where the copies will not overlap. Now, the cases where the copy will not overlap, this is the good case, so we want this to happen, if the sampling frequency is bigger than twice the maximum frequency in the signal. So if omega s is strictly greater than 2 omega 0, is greater than the Nyquist rate, then the copies, the sample signal will look something like this in the frequency domain. So you have multiple copies of the original signal with no overlap, so there is no aliasing. Now if there is overlap, if omega s is strictly less than 2 omega 0s, then these copies are going to overlap and you're going to have a bit of a problem. And we'll see why later. So now, just to tell you why this is happening, so you have this copy, and then you have to add to this copy, so you're going to have a problem in this interval here. So you're going to have this part plus this part, so it's going to be a constant. So this is why you get these kind of things. So this is why you get the constant here, because where the signals are overlapping. And this is here you have aliasing. And aliasing because you're going to see that you're going to have a signal that is different than the signal we started with, but it's going to look like an alias. It's going to, when you sample it, it's going to look like the same, although it's not, and this is why you cannot recover. So meaning, let's suppose you have these samples here, right? So let's do this, right? So one signal could be this, or another signal could be this, right? So these are aliases, different aliases, and you won't be able to differentiate. And in the frequency domain, this is what's happening. Now, the question that I want to answer in the second part is that if we are in the good case, meaning if there is no aliasing here, how can I recover the original signal from just the samples? I'm going to be able to recover the whole signal at any time t exactly with no problem, just from having discrete samples. And this is what I want to answer in the second part, and by answering that, I basically will be proving the sampling theorem.